There is a planet 4 light-years from Earth that may or may not exist, and at this moment nobody on the planet you're sitting on knows which it is. A team of astronomers led by a researcher at NASA's Jet Propulsion Laboratory pointed the James Webb Space Telescope at Alpha Centauri A, the nearest star to ours that resembles our Sun in nearly every measurable property, and after months of careful processing, found a single faint point of light at a position consistent with a Saturn mass world in the habitable zone. 2 months later they looked again. The planet was gone. 2 months after that they looked a third time, still gone. A doctoral student named Aniket Sanghi gave the phenomenon a name that has since travelled through the astronomical press, the case of a disappearing planet. The team's analysis concluded that 52% of dynamically stable orbits consistent with their data would naturally produce exactly that pattern, visible in one epoch, invisible in the next two. The orbit, if real, is eccentric. The orbit, if real, is tilted. The orbit, if real, predicts that the planet should return to view in August 2026, approximately 8 weeks from when you're hearing this. So here is the question that sits in the dark between us and our nearest Sun-like neighbour. What is actually orbiting that star, and will we know within weeks? Settle in, subscribe if you haven't already, and stay with us, because we are about to walk through the most carefully prepared planet hunt in the history of exoplanet astronomy, and the result is currently being decided. Let's begin. Part 1. The Cosmic Front Porch. 4 light-years away, on a clear southern night, you can see it with your own eyes. The third brightest star in the night sky. Brighter than every star most people in the Northern Hemisphere have ever named. Only Sirius and Canopus shine more brilliantly. Its colour is a warm yellow-white, almost identical to the sun setting behind a thin layer of haze. In the constellation Centaurus, it sits low for northern observers, hidden below the horizon for most of the inhabited Earth, but in the southern hemisphere it has been a navigational anchor for thousands of years. Polynesian wayfinders used it. Maori star lore named it. The ancient inhabitants of the southern continent watched it long before any telescope existed to ask what it was. It is called Alpha Centauri, and the thing you need to know, before anything else, is how close it is. 4.37 light-years. In a galaxy roughly 100,000 light-years across, 4.37 light-years is not even 1/10,000th of the journey from one edge to the other. It is, in cosmic terms, the front porch. If our solar system were a single house in a city the size of New York, Alpha Centauri would not be in the next town over. It would not be down the block. It would be the front porch of the house next door, separated from us by a single fence and a small patch of grass. That sounds dramatic. It is supposed to, because nothing else in human experience is as far away as Alpha Centauri, and nothing in the universe is closer to us that resembles us. The light leaving Alpha Centauri tonight will not reach Earth until late 2030. A photon departing that star when you started high school arrives before you finish college. A radio signal sent from one of our deep space dishes today would take just over 4 years to reach the system, and any reply would take another 4 years to come back. By the standards of stellar distance, this is the closest human beings will ever live to another sun. Here is what we mean when we say the system. Alpha Centauri is not a single star, it is 3. Alpha Centauri A and Alpha Centauri B are 2 sun-like stars locked in a long, slow gravitational dance, orbiting their common centre of mass once every 79.9 years. The third member, Proxima Centauri, is a small, dim red dwarf, orbiting the central pair at a vast distance, about 13,000 astronomical units from the centre of the system. Proxima is, technically, the nearest star to Earth, 4.2465 light-years away, closer to us by about 120 light-hours than Alpha Centauri A and B. But Proxima is also a different kind of star entirely. A red dwarf, smaller and dimmer and more violent than our Sun, prone to enormous flares that can strip the atmospheres off any planets it possesses. and Proxima does possess planets. We already know that. In 2016, astronomers using the European Southern Observatory's HARPS instrument confirmed a planet, Proxima b, orbiting Proxima Centauri at a distance of about 5% of the Earth-Sun separation, completing one full orbit every 11 days. It is roughly Earth mass. It sits within the conventional habitable zone of its host star, which sounds wonderful until you remember what kind of star Proxima is. The habitable zone of a red dwarf is so close to the star that any planet inside it is tidally locked, one hemisphere facing the star permanently, the other facing eternal night, and the violent flares of red dwarfs would have stripped any atmosphere Proxima b might once have possessed within a few 100 million years of the system's formation. Proxima b might exist. It almost certainly is not Earth. In 2022, astronomers confirmed a second planet around Proxima, Proxima d, a sub-Earth mass world even closer to the star, well inside the habitable zone but in an environment so hostile that calling it habitable is a courtesy. A third candidate, sometimes called Proxima c, sits at the edge of detection and may or may not exist. For all the excitement about Proxima's planets, the truth is that they are interesting curiosities, not analogues to Earth. The real prize was always the other two stars in the system, Alpha Centauri A and Alpha Centauri B, especially A. Because Alpha Centauri A is not just Sun-like, it is, in almost every measurable respect, identical to our Sun. Same spectral classification, G2V, the exact label astronomers give the Sun. Mass about 1.1 solar masses, radius about 1.2 solar radii, effective surface temperature roughly 5,790 Kelvin, compared to the Sun's 5,778. Age estimated between 4.85 and 5.3 billion years, overlapping with the Sun's age of about 4.6 billion years. From a few thousand light-years away, an alien astronomer trying to tell the two stars apart would have a hard time without spectroscopy. They are siblings. They are, by every measurement we can make from this distance, the closest thing to our own star anywhere in the 4-light-year sphere around us. Alpha Centauri b is slightly different. A K-type star, about 91% the Sun's mass, cooler and smaller, orange rather than yellow. Still Sun-like in the broadest sense, still capable of warming planets the way our Sun warms Earth, but a step removed from A's near-perfect match. For more than 70 years, astronomers have asked one question about this system. Does Alpha Centauri A have planets? It is the most natural question in the field. We have a star almost identical to our Sun, sitting 4 light-years away, in a multiple-star system with a confirmed planet around its dimmer sibling. The expectation, even before anyone had the tools to test it, was that of course Alpha Centauri A should have planets. That is the rule, not the exception. By the time the Kepler Space Telescope was retired in 2018, we knew that planets around Sun-like stars are common. Most G-type stars have at least one. The question was never whether planets should exist around Alpha Centauri A. The question was where they were, and why we could not see them. For 70 years, every attempt to answer that question failed. This is the part that needs explaining. Because Alpha Centauri A is so close, almost embarrassingly close by the standards of exoplanet hunting, the natural assumption is that planets around it should be the easiest in the sky to detect. Nearer objects appear brighter and larger than distant ones. The faintest planet, the kind that vanishes into the background noise around a star 1,000 light-years away, should shine like a beacon around a star 4 light-years away. Proximity, in any reasonable universe, should make detection trivial. But this is not a reasonable universe, and Alpha Centauri A is not a reasonable target. The very things that make it close also make it impossible. Its proximity means we are looking at one of the brightest objects in the entire sky, too bright for most modern instruments to handle directly. Its closeness in space pairs with the closeness of its companion star, Alpha Centauri b, which sits next to it in our view and floods every observation with contaminating light. Its rapid apparent motion across the sky, the fastest of any naked-eye star, at 3.7 arcseconds per year, means it cannot be held still long enough for the precise observations needed to detect faint planetary signals. And its position in the sky places it directly in the plane of our galaxy, where the line of sight cuts through dense fields of background stars and galaxies that any planetary signal would have to be separated from. Every standard exoplanet detection technique that works elsewhere in the galaxy stops working at Alpha Centauri A. The radial velocity method, which measures the tiny wobble a planet induces in its host star, has been pointed at this system for decades. It has ruled out massive close-in worlds. It has not been able to reach the sensitivity needed for a Saturn-mass planet at 2 astronomical units, the kind of planet a Sun-like star is most likely to have at that distance. The transit method, which watches for the brief dimming as a planet passes in front of its host, requires the planet's orbit to be aligned with our line of sight. The orbital plane of Alpha Centauri A and B is tilted 79 degrees relative to us, and the chance of a planet's orbit lying flat enough to produce transits is small. Astrometry, which tracks tiny positional shifts in a star's location as a planet tugs it back and forth, is being attempted by the Gaia mission, but Gaia has not yet reached habitable zone planet sensitivity for nearby stars. Microlensing requires an extraordinarily improbable background alignment, which leaves one method: direct imaging, capturing the planet's own light against the overwhelming glare of its host star, photographing the photons, producing, in essence, a picture of the planet next to a picture of the star. This is the hardest technique in exoplanet astronomy, and Alpha Centauri A is the hardest target it has ever faced. The brightness contrast required to detect a cold, mature gas giant around a Sun-like star is about 10,000 to 1. The planet's light is 10,000 times dimmer than the star's light, sitting at an angular distance from the star that, at this proximity, is well within the diffraction halo of any normal telescope. To capture that 1 part in 10,000 of signal against the 9,999 parts of stellar glare, you need an instrument capable of suppressing starlight by factors of thousands, while preserving planetary light by factors close to 1. For most of the history of exoplanet astronomy, such an instrument did not exist. Then, on Christmas morning 2021, humanity launched a $4 billion telescope to a gravitationally stable balance point 1 million miles beyond the Moon, unfolded its tennis court-sized sunshade, cooled its mirrors to a quarter the temperature of the surface of Pluto, and began collecting infrared light from objects fainter than anything human beings had ever measured. It was called the James Webb Space Telescope, and its primary mission was to study the first galaxies in the universe, light that had travelled for 13 billion years to reach us. Almost nobody initially thought it would point at Alpha Centauri. The conservative path was clear: use Webb for the deep universe, catalogue the earliest galaxies, measure the cosmic dawn. Do not risk a $4 billion instrument by pointing it at one of the brightest objects in the sky, where saturation and scattered light could damage detectors that took 20 years and tens of thousands of engineering hours to build. But there was one astronomer who had a different idea, a veteran researcher at NASA's Jet Propulsion Laboratory named Charles Beichmann. And starting in 2017, before Webb had even launched, Beichmann began arguing that the most powerful telescope ever built, the one designed to study the most distant objects in the universe, could also be turned very carefully to look at the closest sun-like star to Earth, to do something nobody had ever done before, to take a picture of a planet around Alpha Centauri A. Almost everyone told him it was impossible. For a long time, he was wrong about whether it was impossible, and then he was right. What he and his team found in August of 2024 was a single faint point of light beside one of the brightest stars in the night sky. A signal at 5.5 sigma, a planet candidate, a world, perhaps, in the habitable zone of our cosmic next-door neighbour. Then, in February of 2025, the planet vanished. In April, it was still gone. This is the story of what they saw, what they lost, and what is about to happen, within weeks of you hearing this, when JWST looks again. Part 2. Why the closest star was the hardest. To understand what Charles Beichmann was up against, you need to understand the fundamental absurdity at the heart of exoplanet astronomy. The nearest stars to Earth should be the easiest to study. They are not. They are the hardest. The system that lives on our cosmic front porch, the one any reasonable observer would assume astronomers have catalogued planet by planet, decade after decade, has resisted every attempt to be properly seen. Begin with what we know works on stars farther away. The most successful planet detection technique in the history of astronomy is the transit method. You stare at a star, you wait, and if a planet happens to pass between you and the star dims by a tiny fraction of a percent for a few hours. Measure that dimming carefully enough, repeat the observation across multiple orbits to confirm a pattern, and you have a confirmed planet. The Kepler Space Telescope, retired in 2018, used this method to discover most of the nearly 6,000 confirmed exoplanets we now know about. It worked beautifully for distant stars. Transit detection requires a very specific kind of luck. The planet's orbit must be aligned so that its path between you and the star actually crosses the visible disk of the star, from your particular vantage point in space. For most planetary systems, the orbital plane is tilted at random angles relative to our line of sight, and only a small fraction will happen to align so that transits are visible from Earth. For a planet at the Earth-Sun distance around a Sun-like star, the probability is less than 0.5%. For closer-in planets, the geometry is slightly more forgiving, but still small. For Alpha Centauri A, the geometry is essentially hostile. The binary orbit of A and B is inclined 79 degrees relative to our line of sight. That tells us something important about the formation history of the system. In a binary star system, the protoplanetary disk that gives birth to planets is generally aligned with the binary plane, because the disk inherits the angular momentum of the original collapsing cloud, and the binary's orbit is also set by that same angular momentum. So if planets formed around Alpha Centauri A from a disk aligned with the binary plane, they would orbit in approximately the same plane as A and B do, tilted 79 degrees relative to us, almost perpendicular to our line of sight. Transits in that geometry are essentially impossible for habitable zone planets. Even if a planet exists exactly where Earth would be relative to a Sun-like star, the probability of seeing it cross the disk of Alpha Centauri A from our angle is vanishingly small, so the transit method is out. The next workhorse of exoplanet astronomy is the radial velocity method. This works by measuring the tiny back-and-forth wobble of a star as a planet orbits it. The planet and the star both orbit their common centre of mass. The star, being much more massive, moves only a little, but it does move. As the star moves toward us, its light is slightly blue-shifted. As it moves away, slightly red-shifted. Measure those shifts precisely enough, and you can detect the orbital tug of a planet you cannot see directly. This method works on stars that are not too bright and not too active. It has been pointed at Alpha Centauri A for decades. The European Southern Observatory's HARPS instrument, the Las Cumbres Observatory's network, and various other precision spectrographs have all monitored this star. They have ruled out close-in giant planets, the kind that would have shown up as obvious wobbles. They have not been able to definitively detect anything in the habitable zone. The sensitivity required to find a Saturn-mass planet at 2 astronomical units around a Sun-like star is right at the edge of what current radial velocity instruments can achieve, and Alpha Centauri A is bright enough that the signal-to-noise ratio works against the measurement. Saturn-class planets at 2 astronomical units produce stellar wobbles of about 3 or 4 meters per second, at the very limit of detectability. Earth-mass planets at 1 astronomical unit produce wobbles of about 10 centimeters per second, which is well below what any spectrograph can reliably measure today. Radial velocity has not failed to find planets around Alpha Centauri A. It has only failed to find the planets that would be there. What about astrometry? This is the technique that tracks a star's tiny position shifts as it wobbles in response to orbiting planets, the same physical motion that radial velocity captures in spectral shifts, but measured as actual angular displacement on the sky. The European Space Agency's Gaia mission has been measuring stellar positions across the galaxy with extraordinary precision since 2014. In principle, Gaia could detect the astrometric signature of a Saturn-mass planet at 2 astronomical units around Alpha Centauri A. In practice, the mission's full astrometric data release for nearby bright stars is still being processed, and the kind of long baseline analysis needed to pull out the very long orbital periods has not yet been completed. Astrometry is coming. It has not yet arrived for this system at the sensitivity required. So we are down to direct imaging. Direct imaging is the technique that has captured the imagination of the public most successfully. The idea that you might actually photograph a planet around another star. The romance of the technique is that you are not inferring the planet's existence from indirect signals. You're seeing it, catching its photons, recording its light. The romance comes with a brutal physical cost. The light from a planet is not just a little fainter than the light from its host star, it is overwhelmingly fainter. For young hot planets, the kind that still glow brightly from the residual heat of their formation, just a few 100 million years old, the brightness contrast with their host star can be as low as 10,000 to 1 or even less. For mature planets like the ones around Alpha Centauri A, which have had billions of years to cool, the contrast is much worse. A Saturn-mass planet at 2 astronomical units, in radiative equilibrium with its host star, emits its peak thermal radiation in the mid-infrared, around 15 to 20 micrometers of wavelength. Even at those wavelengths where the star's emission is somewhat dimmer than at visible light, the planet is still about 10,000 times fainter than its host. That contrast is the wall. To get over that wall, you need an instrument capable of suppressing starlight by factors of thousands, without suppressing the much fainter planetary light at slightly different positions on the detector. The standard tool for this is called a coronagraph. The name comes from the early 20th century work of the French astronomer Bernard Liot, who built the first coronagraph in 1930 to observe the sun's corona, the faint outer atmosphere that is normally washed out by the blinding disk of the sun itself. Liot's instrument used a physical mask to block the direct sunlight, allowing the much fainter coronal light surrounding it to become visible. The same idea, scaled up and refined over a century, became the modern stellar coronagraph used in exoplanet astronomy. The problem is that no coronagraph is perfect. Every starlight-blocking instrument leaks a little. The leakage takes the form of complex diffraction patterns, bright rings, speckles and fringes spreading out from the blocked star's position, contaminating the field where a planet might be detected. To pull a planet out of that contamination requires extraordinarily careful instrument design, extraordinarily precise pointing, and sophisticated data processing algorithms that subtract the instrument's known systematic patterns while preserving genuine planetary signals. And here, finally, we run into the specific reasons Alpha Centauri A is the hardest direct imaging target ever attempted. The first reason is brightness. Alpha Centauri A is the 3rd brightest star in the night sky, after Sirius and Canopus. Its apparent magnitude is negative 0.01. In astronomical brightness measurements, lower numbers mean brighter objects, and the magnitude scale is logarithmic. Every 5 steps corresponds to a factor of 100 in brightness. A magnitude of negative 0 is at the very high end of what naked eye observers see. For comparison, a 10th magnitude star, well within the reach of small backyard telescopes, is more than 10,000 times fainter than Alpha Centauri A. For modern space-based observatories, that brightness is genuinely dangerous. The fine guidance sensors that lock onto a target star to keep the telescope pointed correctly are designed for typical scientific targets, which are usually much dimmer than naked eye stars. Point the guidance sensors at Alpha Centauri A directly, and they saturate. They receive more light than they can measure. The system cannot determine where the star actually is on the detector, and pointing fails. The telescope cannot lock onto its target. The observation cannot proceed. The second reason is the binary companion. Alpha Centauri B sits, on average, at angular separation of a few arcseconds from Alpha Centauri A, close enough that whenever you point a sensitive telescope at A, B floods the field with its own light. A coronagraph can block one star at a time. It cannot block two stars positioned at different locations on the detector. The scattered light from B contaminates the area around A, where any planet would have to be detected. Removing that contamination requires either intricate computational subtraction or extraordinarily careful timing of observations to catch the binary at moments when B is far enough from A to be partly outside the field. Neither solution is easy. The third reason is the system's proper motion. Alpha Centauri has one of the largest proper motions of any naked-eye star, 3.7 arcseconds per year. That means the system's apparent position on the sky shifts by more than 3 arcseconds every year, by about 3,000ths of an arcsecond every day, by tens of micro-arcseconds every hour. For a telescope trying to hold the star precisely behind a coronagraphic mask for hours-long exposures, that motion is enormous. The pointing must be continuously adjusted with extraordinary precision just to keep the star centered. Any drift, even a few thousandths of an arcsecond per minute, degrades the coronagraph's ability to suppress starlight and floods the field with light leakage. The fourth reason is the galactic plane. Alpha Centauri sits almost exactly in the plane of the Milky Way, looking through the disk of our galaxy toward the constellation Centaurus. Every observation of Alpha Centauri A includes hundreds or thousands of background stars and galaxies along the line of sight. Any detected signal must be carefully distinguished from those background sources. A faint point of light beside Alpha Centauri, A could be a planet orbiting the star, or it could be a distant background galaxy billions of light-years away that happens to align with the star during the observation. Separating real planetary signals from this crowded background requires cross-checking against every astronomical catalogue that exists. Now stack all four problems on top of each other. A star bright enough to damage detectors, a companion bright enough to flood the field, a proper motion fast enough to defeat normal pointing, a background dense enough to mimic any signal you might detect. Then add the requirement of contrast suppression by factors of 10,000 to 1. Then add the requirement that you do all of this without ever having pointed a $4 billion telescope at one of the brightest objects in the sky before. This is the combination that defeated every prior attempt to image planets around Alpha Centauri A. Ground-based telescopes equipped with adaptive optic systems and dedicated coronagraphs spent years trying. The European Southern Observatory's NEAR instrument, Near-Earths in the Alpha Centauri region, a collaboration with the Breakthrough Initiatives, was custom-built for exactly this target, integrated into the Very Large Telescope in Chile, and ran a 100-hour campaign in 2019. It produced one marginal signal, a candidate called C1, at angular separation around 1.1 arcseconds from Alpha Centauri A. Not strong enough to claim a discovery. Most astronomers filed it as an interesting hint requiring better data. Most astronomers also assumed the better data would not come from Webb. Webb was designed to look at the first galaxies in the universe. It was tuned for the faintest objects ever observed, not for the brightest objects in the sky. Its instruments were optimized for the deep universe, not the cosmic front porch. The conservative engineering judgment was that pointing this priceless instrument at Alpha Centauri A was both dangerous and unnecessary. But one researcher believed it was worth attempting anyway. He believed Webb could do what no other telescope had ever done, see with its golden mirrors and its mid-infrared instrument's specialized coronagraph what was actually orbiting our cosmic next-door neighbor. His name was Charles Beichmann, and he had been working on this problem since before Webb existed. Part 3. The Man Who Refused to Give Up. Imagine for a moment that you are a photon. You have just left the surface of Alpha Centauri A. The star is a churning yellow-white sphere about 1.1 times the mass of our Sun, its surface boiling at 5,790 degrees of temperature, granules of convecting plasma rising and falling across a disk the size of 1.2 solar radii. You were created near the surface by the random thermal energy of that plasma, and you have been ejected into the vacuum around the star at the speed of light. You travel outward in a straight line, carrying with you the spectral signature of your star, the absorption lines of hydrogen and calcium and iron, imprinted on you by the layers of cool gas just above the surface where you originated. You're alone, in vacuum, for 4 years and 4 months. You pass through the heliosphere of Alpha Centauri A, the bubble of charged particles surrounding the system. You enter the interstellar medium, the diffuse cloud of gas and dust and cosmic rays that fills the spaces between stars. You travel through a region of space so empty that you might cross the orbit of a planet without noticing it. You continue, undeflected, undisturbed, for 4.37 light-years of vacuum. Then, on the morning of August 14th, 2024, you arrive at a particular point 1 million miles beyond Earth, at the gravitational balance point called Lagrange 2, where a $4 billion telescope is waiting. You strike the primary mirror. The primary mirror is 6.5 meters across. It is hexagonal, 18 gold-coated beryllium segments arranged in a honeycomb pattern, each segment polished to a smoothness that, if scaled up to the size of the United States, would have hills no taller than a few inches. The gold coating is there because gold reflects infrared light efficiently, and infrared is the wavelength range Webb was built to study. You bounce off the primary mirror at a specific angle calculated by the telescope's optical system, and you head toward the smaller secondary mirror suspended above the primary on tripod struts. You strike the secondary mirror. You bounce again, this time downward and inward, through a small hole in the center of the primary, into the body of the telescope. You enter the tertiary optics. You reflect off a fine steering mirror that compensates for any tiny pointing drift. You enter the mid-infrared instrument called MIRI, one of 4 scientific instruments mounted at Webb's focal plane. Inside MIRI, you encounter a coronagraph. The coronagraph is a piece of optical hardware called a 4-quadrant phase mask. It is, physically, a transparent plate engraved with a precise pattern of phase shifts. 2 of the 4 quadrants of the detector field carry a half-wavelength phase shift. The other 2 do not. The geometry means that any light striking the mask at the exact geometric center, light from a star sitting perfectly on the optical axis, interferes destructively with itself as it passes through the 4 quadrants. The phase-shifted halves cancel the unshifted halves. The light disappears. You're arriving from Alpha Centauri A, which has been positioned by an extraordinarily precise pointing maneuver exactly on the optical axis of the 4-quadrant phase mask. You meet the mask. Your wavefront combines with the other photons arriving from the same star center at the same moment. The combined wave cancels itself. You disappear. The detector behind the mask records nothing where you should have been. This is what the coronagraph is for. It exists to make starlight vanish. You, and every other photon from Alpha Centauri A in your particular beam, are the noise that the coronagraph is designed to eliminate. But you are not alone. Somewhere just behind you, leaving the same star system at the same moment, is a different photon. It did not come from Alpha Centauri A. It came from a much fainter object orbiting at 2 astronomical units from the star. A planet, perhaps, glowing in the mid-infrared at a temperature of about -48 degrees Celsius. That photon was emitted into space and travelled the same 4.37 light-years through the same interstellar vacuum to arrive at JWST at the same moment as you. But it arrives at a slightly different angle. Because the planet sits at 1.75 arcseconds from Alpha Centauri A as seen from Earth, the photon from the planet enters JWST's optical system at an angle offset by that small angular distance. It bounces off the primary, the secondary, the tertiary the same way you did. It enters MIRI. It meets the same 4-quadrant phase mask. But because it arrives off-center, it does not interfere destructively. It misses the geometric origin of the mask by exactly the angular distance corresponding to the planet's separation from its star. It passes through the mask, it strikes the detector, it is recorded. This is the entire principle behind direct imaging with a coronagraph. The starlight is destroyed by interference at the mask's optical centre. The planetary light, arriving from a slightly different position, slips through. What was, before the coronagraph, a contrast ratio of 10,000 to 1 becomes, after the coronagraph, something much more like 1 to 1, a manageable signal that can be detected against the background noise of the instrument. You are the noise. The planet's photon is the signal. The 4-quadrant phase mask is the difference between detection and failure. That photon, the one from the planet, does not yet have a name in August 2024. It is one in a billion photons arriving at JWST from the candidate planet, none of them carrying any indication of where they came from or what they prove. In the days that follow, those photons will be processed, calibrated, statistically analysed, and finally identified as belonging to an object designated S1. 5.5 sigma significance. A planet, perhaps, in the habitable zone of our cosmic next door. But before any of that can happen, somebody had to convince the world that pointing Webb at Alpha Centauri A was even worth attempting. That somebody was Charles Beichmann. Beichmann is an astronomer at NASA's Jet Propulsion Laboratory in Pasadena, California, with a joint appointment at the California Institute of Technology. He has spent his career at the intersection of infrared astronomy and exoplanet detection. He worked on the infrared astronomical satellite mission in the 1980s. He helped design and build elements of the Wide-Field Infrared Survey Explorer. He has been involved with virtually every major infrared space mission of the past 4 decades. By the late 2010s, he had been thinking about how to detect planets around Alpha Centauri for most of his professional life. In 2017, Beichmann submitted a proposal to use JWST's MIRI coronagraph to search for planets around Alpha Centauri A. The proposal was, by the standards of telescope time requests, unusual. JWST had not yet launched. The instrument's actual on-orbit performance was unknown. The target was a star far brighter than anything the coronagraph had been characterized against on the ground. The technical concept relied on a method that had never been demonstrated with JWST, a procedure called blind offsetting, in which the telescope would first acquire a manageably bright reference star, then slew sideways through precisely calculated coordinates to place Alpha Centauri A behind the coronagraphic mask without ever pointing at it directly. The technical case was that even though Alpha Centauri A was too bright for JWST's fine guidance sensors to lock onto, it was not too bright for the detectors behind a properly suppressed coronagraph. If you could keep the star centered on the mask would block most of the starlight before it reached the detectors. The detector would see mostly suppressed star and any planets that happened to be present at angular separations where the suppression was effective. The scientific case was that Alpha Centauri A was the nearest Sun-like star to Earth, that any planets there would be the closest analogues to our own solar system, that no other technique could reach the necessary sensitivity, and that JWST was, against all initial expectations, the only existing instrument capable of doing the work. The proposal was approved, the observation was scheduled. In 2023, the team attempted the observation for the first time. It failed. The failure was complete. The data could not be reduced to useful science. The team has not publicly detailed the precise mode of failure, but the result was unusable. The complex sequence of blind offset pointing, coronagraph alignment, integration timing, and instrument calibration broke down somewhere in the chain. The first observation campaign produced nothing. Most teams would have walked away. The technique was experimental. The target was the hardest in the sky. The first attempt had failed. The conservative path forward was to release the JWST time, write up the technical lessons learned, and let some future telescope handle the problem. Beichmann did not walk away. He assembled the team again. They analysed the failure. They went back through the observation design, the pointing procedure, the data acquisition strategy, looking for every weakness. They rebuilt the approach. They modified the blind offset procedure to account for issues the first attempt had revealed. They updated the reference star selection. They refined the timing of the coronagraph alignment. They prepared test observations to validate the rebuilt approach before committing to a full science campaign. That work took most of 2023 and the early months of 2024. By mid-2024, the team had test observations in hand that demonstrated the rebuilt approach worked. The blind offset locked Alpha Centauri A behind the coronagraphic mask with sufficient precision. The integration time was adequate. The data reduction pipeline could handle the brightness and the binary contamination. They requested approval for a full observation campaign. They received it. On August 14th, 2024, JWST executed the campaign. 3 long observation sequences, hours of exposure each. The blind offset performed cleanly. The coronagraph held Alpha Centauri A behind its mask. Data streamed back to the Space Telescope Science Institute in Baltimore at the speed of light. The team waited. The raw images, when they arrived, looked like nothing. They were the noise floor of a coronagraph trying to suppress one of the brightest stars in the sky, while being contaminated by a binary companion and threaded with diffraction patterns from the telescope's hexagonal primary mirror. No human eye could find a planet in those frames. The signal, if it existed, was buried beneath layers of optical clutter that no normal observation produces. Pulling it out would require months of computational analysis. The team began the analysis. What they found, after months of processing, would change what humanity knew about its cosmic next door. But before we get to that, you need to understand what they were actually doing during those months. Because the August 2024 observation did not produce a picture of a planet. It produced raw data that had to be transformed, layer by layer, into something interpretable. And the techniques they used, reference star differential imaging, principal component analysis, injection recovery validation, are not the kind of thing most descriptions of exoplanet astronomy explain in detail. They sound technical because they are. But they are the difference between failure and discovery in coronagraphic observations like this one. And the team's careful, patient, almost obsessive use of those techniques is what made the August 14th observation produce a result that, against every expectation, survived every test it was given, including eventually the most important test of all, the test of disappearance. Part 4. August 14th, 2024. There is a particular kind of patience required for coronagraphic observations that is unlike anything else in observational astronomy. It is not the patience of a long-exposure photographer waiting for darkness. It is not the patience of an animal observer waiting for a creature to appear. It is the patience of someone who has spent years preparing for an observation that, when it finally arrives, produces data that look like nothing, and then has to be turned, through months of computational work, into the answer to a question 70 years old. On August 14th, 2024, JWST executed the rebuilt Alpha Centauri A observation campaign. The actual observation took only a few hours of telescope time. The preparation had taken roughly 7 years. The analysis would take another 4 months. The observation itself was structured as 3 long sequences. Each sequence began with the telescope acquiring its reference star, Epsilon Muscae, a red giant of spectral class K43, located approximately 330 light-years from Earth in the southern constellation Musca. Epsilon Muscae was chosen because it sits relatively close to Alpha Centauri on the sky, because its brightness, apparent magnitude about 4.1, is manageable for JWST's fine guidance sensors, and because it does not have any nearby companions or contaminants that would complicate the offset slew. It was, in essence, the safe star that JWST could lock onto without difficulty, and from which the more dangerous target could be reached by precisely calculated motion. The fine guidance sensors locked onto Epsilon Muscae. The pointing stabilized. The telescope was now holding still, with the red giant centered on its guidance camera, 4 billion miles from the engineers who had built it. Then, on command, the telescope began its offset slew. The offset was not a simple point at Alpha Centauri now instruction. It was a precisely computed maneuver, calculated for the exact moment of observation, that accounted for several effects. First, the natural angular separation between Epsilon Muscae and Alpha Centauri A in the sky. Second, the parallax shift in Alpha Centauri's apparent position due to the orbital position of L2 around the Sun on August 14th. At 4.37 light-years, Alpha Centauri's apparent location shifts by hundreds of milliseconds depending on Earth's orbital position. Third, the proper motion of Alpha Centauri across the sky since the most recent measurement, 3.7 arcseconds per year, or about 1/100th of an arcsecond per day, which the team had to track and correct for. Fourth, the geometric layout of the Miri coronagraph relative to the telescope's overall pointing, ensuring that the offset placed Alpha Centauri A precisely on the geometric centre of the four-quadrant phase mask. That calculation had to be right to within about 20 milliseconds. That is a small angle. 1 arcsecond is 1/3600th of a degree. 20 milliseconds is 1/180,000th of a degree. The width of a quarter held about 1 mile away. The accuracy required to place Alpha Centauri A precisely behind the mask was the angular equivalent of hitting a quarter from a mile away, except that the telescope was 1,000,000 miles from Earth and operating in vacuum and could not be physically adjusted by anyone. The offset executed. The telescope's fine steering mirror compensated for the residual drift. The blind motion landed Alpha Centauri A on the F1550C mask. The coronagraph engaged. Starlight from Alpha Centauri A, billions of photons per second arriving at the primary mirror, bouncing through the optics, entering Miri, met the phase mask at its geometric centre, interfered destructively with itself, and disappeared. The detector behind the mask began collecting photons. For hours the integration proceeded. The detector counted the few hundred photons per second that leaked past the coronagraph from Alpha Centauri A. It counted contamination from Alpha Centauri B, scattering across the field. It counted photons from background stars in the galactic plane, and, if any planet existed at the right separation and position angle, it counted photons from that planet too. Perhaps a few thousand over the full integration, mixed in with all the other contamination, not yet distinguishable from the noise. 3 sequences, each one a different orbital position of L2 around the Sun, providing slightly different geometry for the binary contamination subtraction. Each one a different roll angle of the telescope, providing different patterns of diffraction structure for the data reduction to work against. Each one a few hours of integration. The total observation time on Alpha Centauri A was approximately 10 hours across the campaign. When the sequences finished, the data was transmitted back to Earth. The raw images arrived at the Space Telescope Science Institute. The team began processing. Here is what the raw images looked like. In each frame, Alpha Centauri A occupied the geometric center of the field, theoretically suppressed by the coronagraph, but in practice still leaking some residual starlight that produced a complex pattern of diffraction rings extending outward from the position of the star. The patterns came from JWST's hexagonal primary mirror, 18 segments creating 6-fold symmetric diffraction spikes, plus the secondary mirror's tripod supports producing additional structures. The coronagraph itself, while suppressing the bulk of the starlight, produced its own characteristic pattern of phase mask edge effects, bright streaks at the boundaries between the phase-shifted and unshifted quadrants, plus an inner working angle below which detection was effectively impossible. Overlaid on the diffraction structure was the scattered light from Alpha Centauri B, which sat tens of arcseconds away from A in the August 2024 observation, but still scattered a halo of contamination across the entire field of view. The halo had a different geometric structure than the diffraction from A, and the data reduction would need to subtract A's diffraction pattern and B's scattering halo separately. Threaded through all of this were the background sources, faint stars and galaxies in the galactic plane that produced point-like signals in random positions across the field. Most were known objects that had been catalogued by Gaia and previous surveys. Some were below the detection threshold of any prior survey and would appear in the JWST data for the first time. If a planet existed at angular separation around 2 astronomical units from Alpha Centauri A, it would produce a signal in the data that would look essentially identical to a faint background source. The only way to distinguish a planetary signal from a background contamination was to verify that the signal was not catalogued elsewhere, did not move with the background field, and did appear in roughly the same position across all 3 observation sequences. No human eye could find that signal directly. The raw images were a mess of overlapping structures, and the planetary signal, if present, was buried at a level orders of magnitude below the contamination. What was required was reference star differential imaging. This technique relies on a simple but powerful idea. If you observe other stars under identical instrumental conditions, same coronagraph, same integration time, same telescope configuration, those reference observations will show you exactly what the instrument does when no planet is present in the field. The diffraction patterns will be there. The scattered light from binary companions will be there if the references are also binaries. The detector noise structure will be there, but there will be no actual planet around any of the reference targets, because the references are chosen to be planet-free or at angular separations where any planets would be too far to register. The team observed several reference stars during separate JWST campaigns, building up a library of templates that captured the systematic behavior of the F1550C coronagraph across different stellar properties. To process the Alpha Centauri A data, they aligned each reference image to the Alpha Centauri A pointing, scaled it to match the brightness ratio between the reference star and Alpha Centauri A, and subtracted it from the science image. What remained, in principle, should be only the contribution specific to the Alpha Centauri A field, including any planets that happen to be present. The reference subtraction removed the dominant patterns of contamination. The data became cleaner, but residual structure remained, patterns that the reference subtraction could not eliminate because they varied subtly between observations in ways that could not be matched precisely. For those residuals, the team used a method called principal component analysis. The idea is to decompose the ensemble of reference observations into a series of orthogonal patterns, ordered by how much variance each pattern explains across the ensemble. The first principal component captures the dominant systematic, the dominant mode of variation between observations. The second captures the next strongest mode, the third captures the next, and so on. The team could then choose to remove a chosen number of principal components from the science image, stripping away systematic noise while preserving signals that did not correlate with any of the removed components. Choosing how many components to remove was a careful balance. Too few, and residual contamination remained that could swamp any planetary signal. Too many, and the algorithm began to remove the planetary signal itself along with the noise. The team calibrated the choice through injection recovery testing. They took raw data from earlier observations of empty fields and inserted synthetic planetary signals at known positions and brightnesses. They then ran the data reduction pipeline and verified that the pipeline recovered the synthetic signals at their known positions with the correct brightnesses without distortion. The number of principal components removed was set at the level where the recovery was reliable and the residual contamination was minimized. Layer by layer, the data reduction proceeded. The September, October, November weeks of 2024 were spent inside this process. The team ran the pipeline against the August data repeatedly. Each run produced incrementally cleaner images. The contamination from Alpha Centauri B was stripped away. The diffraction structure from JWST's primary was subtracted. The background sources were catalogued and either confirmed as known objects or flagged for further investigation, and then, in one particular run, at a particular angular position around Alpha Centauri A, a faint point of light remained after every contamination had been removed. It sat at 1.75 arcseconds east of the star. At the distance of Alpha Centauri, That angular separation corresponded to a projected physical separation of about 2 astronomical units, the distance of Mars from the Sun. The signal was point-like, consistent with a planet rather than an extended dust cloud. Its brightness at 15.5 micrometers was about 3.5 milliansky. That contrast against Alpha Centauri A's host star brightness of around 35,000 milliansky was about 10,000 to 1, exactly the regime the coronagraph was designed to operate in. The team designated the object S1. The next question was whether the signal was real. A single detection, even at the careful 5.5 sigma level the team would eventually report, could in principle be the result of statistical noise, instrumental artifact, or background contamination. The team began the validation process. They cross-referenced S1's position against the Gaia mission catalogue. Gaia has measured the precise positions and motions of nearly 2 billion stars across the Milky Way. If S1 were a background star in the line of sight, it would almost certainly appear in the Gaia catalogue. No catalogued source matched. They examined archival imaging from previous space and ground-based observations of the same field, Hubble Space Telescope archives covering decades of imaging, Spitzer Space Telescope mid-infrared observations, ground-based deep imaging from various survey programs. None showed any object at S1's position that was compatible with the August 2024 detection brightness. They split the August 2024 data into independent halves and ran the reduction pipeline against each half separately. If S1 were a genuine astronomical source, it should appear in both halves at consistent flux and position. If it were a fluctuation in detector noise, the two halves would show different patterns. Both halves produced S1 at consistent flux and position. They performed motion analysis to check whether S1 shifted position across the few hours of integration on August 14th. A nearby moving object, an asteroid for example, would shift position measurably during the observation window. S1 did not shift. It remained stationary relative to Alpha Centauri A, ruling out solar system objects passing through the field. They performed injection recovery on synthetic signals at S1's position, verifying that the pipeline could distinguish real signals from artifacts by inserting fake planets at known positions, and confirming that the pipeline recovered them at the correct positions, with the correct brightnesses, and that the recovered signals behaved in the same way as S1 behaved in the actual data. The behavior matched. Each test S1 passed strengthened the case that the signal was real. By late 2024, the team had eliminated every plausible alternative they could think of. S1 was not a Gaia-catalogued background source. It was not in any archival imaging. It was consistent across split-half analysis. It did not move during the observation. It behaved identically to synthetic planetary signals injected into similar data. What remained was the possibility that S1 was either a previously uncatalogued background source, a galaxy or compact object that had simply never been observed before, because no telescope had ever pointed at this specific field at this depth, or that S1 was a genuine planet around Alpha Centauri A. The team could not yet distinguish those two possibilities from a single detection epoch, but the planetary interpretation was strongly favoured on the joint probability of all the validations passing simultaneously, and on the fact that no plausible background source had been identified despite exhaustive searches. In a quiet workspace at the Space Telescope Science Institute in late 2024, a young doctoral student named Aniket Sanghi sat watching the pipeline finish its run on the August data. The terminal printed a number, 5.5 sigma, at 1.75 arcseconds east of Alpha Centauri A. He looked at it for a long time. For 70 years, astronomers had hoped this number would one day exist. The closest Sun-like star to Earth, 4.37 light-years away, the cosmic next door. Its planetary status had been the open question for as long as planets had been known to exist around other stars. Every prior attempt had failed. Bateman's first attempt had failed. The very fact of attempting it had been controversial, considered by many to be beyond what JWST could realistically achieve. The number existed now, 5.5 sigma, 3.5 millijansky at 15.5 micrometers, effective temperature around 225 Kelvin, mass somewhere between 90 and 150 Earth masses, comfortably in Saturn's class. At an orbital distance comparable to Mars from the Sun, around a star almost identical to our own, 4.37 light-years from where the listener is sitting, a candidate planet, inside the habitable zone of our nearest sun-like neighbour. For 70 years the answer had been unknown. The answer began to exist that morning. The team prepared to publish, but first they wanted confirmation. A single observation epoch, however carefully validated, could not by itself prove a planet existed. The signal needed to be seen again at a different position consistent with orbital motion before the team could claim a discovery rather than a candidate. That confirmation would require follow-up observations. The follow-up was scheduled for February 2025, and when February arrived, the planet was gone. Part 5. The Disappearance. The follow-up observations did not have to wait long. The Space Telescope Science Institute, which operates JWST, maintains a small allocation of telescope time called Director's Discretionary Time. This pool exists for observations of extraordinary scientific value that cannot wait for the normal proposal cycle, which runs about once a year and takes months to evaluate. The candidate planet around Alpha Centauri A qualified without debate. Within weeks of the team submitting the formal request, Director's Discretionary Time was approved. 2 follow-up observation campaigns were scheduled, one in February 2025, the other in April. The reasoning was straightforward. If S1 was a real gravitationally bound planet around Alpha Centauri A, it should appear at different positions in different epochs as it moved along its orbit. The angular distance and direction of a motion between epochs would constrain the orbital period and geometry. With 3 observations across roughly 8 months, August 2024, February 2025, and April 2025, the team could begin to map the orbit. A clear pattern of motion would essentially confirm the planetary interpretation. A clean failure to detect anything at any of the predicted positions would force the team to reconsider. The February observation was scheduled for early in the month, with the same blind offset approach using Epsilon Muscae as the guidance reference, the same coronagraphic mask, the same integration time, the same data reduction pipeline. The goal was to reproduce the August observation as exactly as possible, varying only the calendar date and the planet's expected orbital position. The observation executed cleanly. Every system on JWST performed within specification. The blind offset slew placed Alpha Centauri A on the F1550C mask with the required precision. The coronagraph achieved expected suppression. The integration completed without any anomalies. The data downlinked to STSCI on the standard timeline. The team began the analysis with the same care they had applied in August. The reference subtraction proceeded. The principal component analysis stripped away systematic patterns. The cleaned image emerged. The field where S1 had blazed at 5.5 sigma 5 months earlier was empty. The team double-checked the analysis. They reran the pipeline with modified parameters. They tried alternative algorithms. They examined the raw data directly. They cross-checked the offset coordinates against the parallax-corrected predictions, making sure they had pointed JWST at the right location. They verified that the integration time had been sufficient to reach the same sensitivity as August. They checked the coronagraph alignment quality. They re-examined the reference templates. Every check confirmed that the observation had been executed correctly and that the data was good. S1 was simply not there. In a workspace at the Space Telescope Science Institute, Aniket Sanghi stared at the empty field on his screen. He had personally led much of the August data analysis. He had watched the pipeline produce that 5.5 sigma detection. He had been part of the team that built and validated the analysis pipeline against every plausible failure mode they could imagine. The pipeline had not changed. The instrument had not changed. The target was the same star. The processing was identical, and the planet was gone. He pulled up the August data again and ran the analysis side by side with the February data. The August field showed S1 at 1.75 arcseconds east of the star, 3.5 millijansky, the same signal he had seen for months. The February field showed nothing where S1 should have been. Nothing at 3 sigma, nothing at 2 sigma. Just the noise floor of an excellent coronagraphic observation that contained no detectable planet anywhere within its sensitivity range. The contradiction was complete. The August observation, validated against every test the team could construct, had produced a 5.5 sigma detection of a candidate planet at a specific position. The February observation, executed with identical instrumentation and processing, had produced no detection at the same position or anywhere else. The team discussed possibilities. Maybe February was an unlucky epoch. Maybe some transient condition had reduced sensitivity. Maybe a calibration issue had affected the specific date. The April observation, 2 months out, would offer another chance. They waited. In April, the observation was scheduled, executed, downlinked, and analysed. The result was identical. No 5 sigma detection. No 3 sigma detection. Nothing where S1 should have been. Nothing anywhere else in the coronagraph sensitivity range. The April data was as clean a non-detection as the February data had been. 2 follow-up observations, both technically clean, both well within the sensitivity required to recover the August detection if S1 was still at its August position. 2 confirmed nulls. The candidate planet had vanished. It was at this point that Aniket Sanghi gave the phenomenon the name that would travel through the astronomical press, the case of a disappearing planet. Planets do not disappear. That is the cornerstone of orbital mechanics. A gravitationally bound object orbiting a star follows a path determined by Newton's laws and Einstein's refinements. The path is closed and predictable. Even on a highly elliptical orbit, the planet must appear somewhere in the sky at every moment, never simply vanishing into non-existence. If S1 was a real planet, it had not stopped existing between August and February. It was still out there, somewhere, orbiting Alpha Centauri A. The question was why JWST could not see it. 3 possibilities sat on the table. The first was the most deflating. The August detection had been a statistical fluke that fooled every test. Despite passing cross-references against Gaia, archival imaging, split-half analysis, motion checks, and injection recovery validation, the 5.5 sigma detection might represent a genuine but extraordinarily improbable noise fluctuation. At 5.5 sigma, the probability of random noise producing such a strong signal is less than 1 in 10 million under standard assumptions. But 1 in 10 million events do occur. The universe contains enough observations that even extraordinarily rare coincidences must happen somewhere. Perhaps Alpha Centauri A was the somewhere. The second possibility was a background source. The August detection might have been a genuine astronomical signal, but from a previously uncatalogued object that happened to align with the field of view in August 2024. If that background object had measurable proper motion of its own, a fast-moving star or a transient source like a distant supernova or active galactic nucleus, it might have drifted out of the field by February. The Gaia catalogue cross-reference had ruled out known stars at S1's position, but it could not rule out objects too faint to have been catalogued. The August signal might have been the brief detection of a passing background object that subsequent observations would naturally miss. The third possibility was the most scientifically interesting. S1 was real. It had moved. For this possibility to work, S1 would have to have moved to a region of the sky where Miri's coronagraph could not see it. There were 2 ways that could happen. One was geometric. If the planet moved to a position behind or in front of Alpha Centauri A, from JWST's perspective, it would be hidden by the star itself. The probability of this kind of alignment depends on orbital parameters, but for some orbital geometries it is non-negligible. The other way was instrumental. The F1550C 4-quadrant phase mask does not have uniform sensitivity in all directions around the blocked star. Some position angles around the mask achieve excellent suppression, and allow easy detection of faint planets. Other position angles achieve less suppression, or interact with the geometry of the mask in ways that effectively blind the instrument at certain locations. A planet sitting at one of those low-sensitivity position angles would be undetectable, even at separations where, in principle, detection should be possible. The two effects could combine. A planet on an elliptical orbit moves through different separations and different position angles continuously. At some orbital phases, it would sit at a favourable separation with a favourable position angle, and the coronagraph would see it clearly. At other phases, it would either approach too close to the star or sit at an unfavourable position angle, and the coronagraph would go blind. If S1 was a planet on a sufficiently eccentric orbit, the August 2024 observation might have caught it at a favourable phase, when the planet was near its maximum distance from Alpha Centauri A, what astronomers call a pastron, and at a position angle the coronagraph could resolve. The February and April 2025 observations might have caught it at unfavourable phases, when it was either too close to the star or at a position angle where the coronagraph could not pull its signal out of the noise. If that hypothesis was right, the non-detections were not evidence against the planet. They were evidence that the planet had moved to a part of its orbit where current technology could not follow. But to test the hypothesis, the team needed to do something they had not yet done. They needed to construct a model of what orbits were even possible for S1, given the constraints of the binary system and the observational data they had. That model was the next step. It would take the august detection, combine it with another piece of data they had not yet given enough weight, and produce a forecast that would either reconcile the disappearance or confirm it as a permanent loss. The other piece of data was a faint signal that had been recorded at the Very Large Telescope in Chile, 5 years before JWST ever looked at Alpha Centauri A. It had a name too. The team had been calling it C1, and in late 2024, as the disappearance of S1 settled into the team's working analysis, they began to look at C1 again, with new eyes, and with the possibility that 5 years apart, two completely different telescopes on two different continents had been seeing the same body. Part 6. The Ghost from 2019. 5 years before JWST detected S1 on a mountain in northern Chile, another telescope had pointed at Alpha Centauri A and seen something. The mountain is called Cerro Paranal. It rises out of the Atacama Desert in northern Chile to an altitude of 2,635 meters, in a region that ranks among the driest places on Earth. The dryness is the point. Water vapor in the atmosphere absorbs infrared light, and the dryness of Paranal means the air above the telescopes is thin and transparent at infrared wavelengths, in a way that almost nowhere else on Earth can match. The European Southern Observatory chose this location precisely because of that dryness. Beginning in the late 1990s, ESO built the Very Large Telescope on Cerro Paranal, a complex of 4 8-meter telescopes operating in concert, sometimes individually and sometimes interferometrically combined, that together form one of the most powerful ground-based observatories in the world. In 2019, one of those 8-meter telescopes was equipped with an experimental instrument called NEAR. The acronym stood for Near Earths in the Alpha Centauri region. The instrument was a custom thermal infrared coronagraph, designed and built specifically for the purpose of searching for planets around Alpha Centauri. Its construction was funded in part by the Breakthrough Initiatives, a private philanthropic organization founded by the Russian billionaire Yuri Milner, with the stated goal of accelerating the search for life beyond Earth. The Breakthrough Initiatives had committed substantial resources to several projects aimed at characterizing Alpha Centauri's planetary system, including the more famous Breakthrough Starshot concept that proposed launching gram-scale spacecraft to the system at 20% of the speed of light. NEAR was a more modest, more immediately practical project. Instead of building a starship, build the best possible Earth-based instrument for finding planets around the destination star. The NEAR campaign in 2019 accumulated approximately 100 hours of integration time on Alpha Centauri A. That is an enormous investment of telescope time at a major observatory. By comparison, The JWST observation of August 2024 totaled roughly 10 hours. The parallel observations were, in raw integration time, 10 times longer. But ground-based observations face a fundamental limitation that space-based observations like JWST do not. The Earth's atmosphere distorts incoming light. Even at the driest, highest, most transparent observing site on Earth, the air above the telescope is in constant motion, with cells of slightly different temperature and density acting like irregular lenses that randomly bend incoming light by small amounts. The technique called adaptive optics, which the VLT employs aggressively, partially corrects for this distortion by measuring the wavefront of light from a guide star many times per second and using deformable mirrors to actively cancel out the atmospheric distortion in real time. Adaptive optics is one of the great triumphs of modern observational astronomy. It does not work perfectly. Residual atmospheric speckle, the tiny scintillations that adaptive optics cannot remove, creates faint signals that mimic point sources in coronagraphic data. NIRS data reduction, applied to the 100 hours of integration on Alpha Centauri A, produced a single marginal point source. It sat at angular separation approximately 1.1 arcseconds from the star. The team designated it C1. C1 was not strong enough to claim as a confirmed detection. The signal-to-noise ratio was not high enough to rule out residual atmospheric speckle. The team's published analysis presented C1 as a candidate worth following up, an interesting hint that future observations should investigate, rather than as a discovery. Most astronomers filed it away as exactly that, an interesting hint. Better data required. By the time JWST detected S1 in August 2024, C1 had been sitting in the literature for 5 years, largely forgotten. It had not appeared in major review articles. It had not driven new observation campaigns. The NIR experiment itself had concluded its initial campaign and moved into a more limited operational mode. The breakthrough initiatives had continued to fund related work but had not made C1 a centerpiece of their public messaging. Then S1 appeared. When the Bachmann team began their analysis of the August 2024 data and the candidate at 1.75 arcseconds emerged, they naturally examined whether any previous observations had detected anything in the same region. The Gaia catalogue cross-reference in the archival imaging review had been comprehensive. They had not initially given particular weight to the C1 signal, because C1 had been at a different angular separation from Alpha Centauri A. The S1 detection sat at about 2 astronomical units projected. C1 had sat at about 1.2 astronomical units projected. A static object cannot appear at both positions. The team had treated C1 and S1, in their initial analysis, as separate phenomena. The disappearance of S1 in February and April 2025 changed that calculation. If S1 was a real planet on an eccentric orbit, the disappearance hypothesis required that the planet had moved between the August 2024 detection and the February 2025 non-detection. The motion would have to be consistent with a closed gravitationally bound orbit around Alpha Centauri A. If the planet's orbit was sufficiently eccentric, the planet could be at one position in one epoch and a substantially different position in another epoch. If the orbit was eccentric enough and oriented in the right way, it could pass through a position at 1.2 astronomical units from the star in 2019 and a different position at 2 astronomical units from the star in August 2024. 5 years of orbital motion separating the two epochs. That would mean C1 and S1 were not separate phenomena. They were 2 epochs of observation of the same body. The team began to explore this possibility seriously. The key check was whether a single orbit could simultaneously satisfy 3 conditions. First, it had to pass through approximately 1.2 astronomical units from Alpha Centauri A at the time of the NIR observations in 2019. Second, it had to pass through approximately 2 astronomical units from Alpha Centauri A at the time of the JWST observation in August 2024. Third, it had to be dynamically stable in the presence of the binary companion Alpha Centauri B which over millions of years would otherwise destabilize and eject any planet on an unsuitable orbit. The first two conditions could be satisfied by many possible orbits. The third condition was much more restrictive. Stability in a tight binary system constrains where a planet can survive over the system's lifetime. Planets on certain types of orbits would be slingshot out of the system within a few million years. Others would survive, but with their orbital parameters slowly modified by gravitational interactions with the binary companion. Only a specific family of orbits would remain stable for billions of years and also pass through both the C1 and S1 detection positions. The team built a simulation framework to search this orbital parameter space. The framework generated millions of synthetic orbits, each constrained by the C1 and S1 positions, and each tested for dynamical stability over a 5 billion year timescale, comparable to the age of the Alpha Centauri system. Orbits that failed the stability test were discarded. Orbits that did not pass through the required positions were discarded. What remained was a family of solutions, a set of orbits that satisfied all three constraints. The family was not a single orbit, it was a range of orbits. Different combinations of orbital period, eccentricity, inclination, and orientation could all produce the required C1 and S1 positions while remaining stable. But the range was bounded. The orbits clustered within a specific region of parameter space, and the boundaries of that region were informative. The orbital period of the surviving family clustered between 2 and 3 Earth years. That is much shorter than Jupiter's 12-year orbit, but longer than Mars's roughly 2-year orbit around the Sun. For a planet at the inferred average distance from Alpha Centauri A, that orbital period was consistent with Kepler's laws given the mass of the host star. The eccentricity of the surviving family clustered around 0.4. That is a striking number. Our solar system's planetary orbits are nearly circular. Earth's eccentricity is 0.017. Mars sits at 0.093. Even Mercury, the most elliptical of the major planets, reaches only 0.206. An eccentricity of 0.4 exceeds anything in our planetary neighbourhood except certain dwarf planets and short-period comets. Comparing to a comet might overstate the case, but the comparison is apt in form. This is not a gentle near-circular orbit. This is a dramatic looping path that swings between perihelion at about 1 astronomical unit from Alpha Centauri A and apastron at nearly 2 astronomical units. The inclination of the surviving family, measured relative to the plane of the Alpha Centauri A and B binary, clustered between 50 and 130 degrees. The full range was wider than the eccentricity range, partly because the available data was not yet sufficient to constrain inclination as tightly. But even the most favourable inclinations were substantially misaligned with the binary plane. The standard expectation from planet formation theory is that planets in a binary system form in a disk aligned with the binary's orbital plane. A misalignment of 50 degrees or more is a significant departure from that expectation. Two things became clear from the orbital analysis. The first was that the eccentric inclined orbit family naturally explained the disappearance. The team ran the surviving orbits forward from August 2024 to February 2025 and April 2025, asking, of the orbits that satisfy the C1 and S1 detection constraints, what fraction would place the planet at undetectable positions in the follow-up epochs? The answer was 52%. 52% of dynamically stable orbits compatible with the C1 and S1 positions placed the planet, in February and April 2025, either at a separation too close to Alpha Centauri A for the coronagraph to resolve, or at a position angle where MIRI's 4-quadrant phase mask had low sensitivity. The non-detection was statistically more probable than detection. The disappearance was not evidence against the planet. The disappearance was the most likely outcome given the orbital constraints. The second realization was that the orbit's eccentricity and inclination, taken together, told a story about the planet's history. A planet that condenses from a protoplanetary disk inherits the disk's geometry, a nearly circular orbit lying in the disk plane. To produce an eccentric inclined orbit, Something would have had to act on the planet after its formation. Something would have had to disrupt its initial conditions. Several mechanisms could explain it. A close gravitational encounter with another planet, possibly one that was subsequently ejected from the system or fell into the star. A long-term gravitational interaction with the binary companion through what is called Kozai-Ledoff oscillation, a resonant exchange of eccentricity and inclination that can develop over millions of years in any planetary orbit sufficiently misaligned with a stellar companion's plane. Migration through a misaligned disk during the system's first 100 million years. Whichever mechanism was responsible, the implication was the same. S1, if it existed, had not been left undisturbed since its formation. Something had acted on it. Something had kicked it. The eccentric, inclined orbit was the signature of a violent dynamical history written into the geometry of the planet's path. Billions of years later, the wound was still visible. The path of the planet across its host star's sky was the record of an event that had happened in the system's first 100 million years and shaped the planet's existence for every orbit since. S1, if real, was not a quiet, undisturbed neighbour. It was a survivor. It had lived through whatever had tilted its orbit and inflated its eccentricity, and it had persisted in that configuration ever since, swinging between perihelion and apastron once every 2 to 3 Earth years, moving through detectable and undetectable orbital phases, on a schedule the team had now begun to map, and the map gave them a forecast. If the disappearance was a temporary consequence of orbital phase, the planet should become visible again at a predictable future date. The same simulation framework that had explained why February and April 2025 were unlikely to yield detections also predicted when the next favourable window would open. The forecast was specific: August 2026, approximately 24 months after the original detection. Almost exactly one orbital cycle later, given the inferred period of 2 to 3 years, the planet would have returned to a position similar to where it was in August 2024. The coronagraph would be able to resolve it again. The signal should reappear. The forecast was a prediction. It was also a trap. If the August 2026 observation reproduced the detection at the position predicted by orbital motion, at a brightness consistent with the August 2024 signal, the case for a real planet would become essentially overwhelming. 2 separate epochs of detection at orbitally consistent positions, separated by the predicted interval, with C1 as a 5-year prior precursor at a compatible position, would together rule out the alternatives. The August 2024 signal had been validated extensively. A second detection at the predicted position would close the door on the remaining alternatives. If the August 2026 observation produced nothing, the team would face a different kind of trap. Either the orbital model was wrong, the surviving family of orbits did not actually represent S1's path, and the August 2024 signal would need to be reinterpreted. Or the alternative hypotheses, especially the statistical fluke possibility, would begin to look more plausible. The team would have to either revise the orbital parameter range substantially, requiring additional observations to find the planet, or concede that the August 2024 detection might, despite passing every test it was given, have been an extraordinarily improbable noise fluctuation. Both outcomes were scientifically valuable. The team submitted the orbital analysis for publication in the Astrophysical Journal Letters in 2 companion papers. The first, with Aniket Sanghi as co-first author along with Bachmann, covered the observations and the orbital and physical properties of the candidate. The second, with Bachmann as lead author, covered the binary star modelling, the planet and exozodi search, and the detailed sensitivity analysis. The papers appeared on the ArcSiv preprint server in August 2025, 1 year exactly after the original detection. The team gave them the collective title Worlds Next Door, and the 2 papers became, almost overnight, among the most discussed exoplanet papers of the year. The team then waited for August 2026. That was last year, from the perspective of the team's planning. From the perspective of this video, August 2026 is about 8 weeks away. The next chapter of the story is one neither the team nor the listener has yet been able to read. Part 7. The August 2026 window. Here is the strange and singular fact at the centre of this story. Today, as you listen to this, the answer does not yet exist. For nearly every other story this channel has ever told, the events that anchor the narrative happened long ago. The death of Voyager 1's plutonium power source, the detection of the WOW signal in 1977, the Carrington event in 1859, the collapse of H.L. Tau's protoplanetary disk into the rings ALMA captured in 2014. The Halo Drive thought experiments published years before any current telescope could test them. These are stories whose endings, however incomplete, are already in the record. The science continues to evolve, but the central events have already happened. The data already exists. The interpretation may be open. The events are not. S1 is different. The most probable future date for the resolution of this story sits about 8 weeks ahead of the moment you're listening to this. By the time some of you watch this video, the observation that will decide the case will have already occurred. The data will already exist. The analysis will have begun. The answer will be quietly settling into the literature, into press releases, into the next generation of textbooks. For others of you, the window will still be open. JWST will not yet have looked. The team will be in their final preparation phase. The blind offset procedure will be queued. The reference star Epsilon Muscae will be sitting on the southern sky, waiting to anchor the next observation. The detector will be cooling on its standard schedule. The pipeline will be primed for fresh data. For at least some of you, you will hear the answer arrive while this video is still in your watch history. You will see the headline on a news feed. The closest Sun-like star to Earth has a confirmed planet, or it does not. The answer will come. This is unusual for a sleep-friendly documentary. Most videos of this genre tell stories about events that are settled. The S1 candidate is unsettled in a particular way that almost never happens. The instruments that will decide it have been pointed in advance. The orbital predictions are fixed. The team is waiting. The result will arrive without ambiguity within months of this video's release. The mechanics of the next observation are straightforward, because the team has now executed this procedure successfully 3 times. Once in August 2024, producing the original detection, once in February 2025, producing the first null, and once in April 2025, producing the second null. The procedure has been tested, refined, and validated. The team knows what works. The blind offset will use Epsilon Muscae as the reference, the same red giant that anchored the previous observations. The pointing will execute through precisely calculated coordinates that account for Alpha Centauri's continuing proper motion across the sky and for the parallax shift in its apparent position relative to L2's August orbital position around the Sun. The F1550C4 quadrant phase mask will engage. The integration will run for approximately 10 hours across multiple sequences, mirroring the August 2024 exposure depth. The data will downlink to STSCI on the standard timeline. The analysis pipeline, now extensively validated with months of refinement since the original detection, will begin its run. The orbital prediction is specific, based on the surviving family of orbits compatible with C1 in 2019 and S1 in August 2024. The most probable next visible epoch falls in August 2026, with secondary probability extending into early autumn. The planet, if it exists, should be approaching a pastron again, returning to a position similar to where it was 2 orbital cycles earlier. The angular separation from Alpha Centauri A should be in the range of 1.5 to 2 arcseconds. The brightness, if the planet's atmospheric properties have not changed, should be comparable to the original 3.5 milliansky detection. The position angle, the direction from Alpha Centauri A in which the planet sits, should be different from the August 2024 position by an amount consistent with the inferred orbital geometry. A clean detection within those parameters would essentially close the case. 2 epochs of detection separated by the predicted interval, at positions consistent with orbital motion, with the C1 signal serving as a 5-year prior precursor at a compatible orbital phase, would together eliminate the alternatives that the team has been unable to fully rule out. The statistical fluke explanation would require that 2 independent observations across 2 years, executed with extraordinary care and validated extensively, both happen to produce signals at exactly the positions and brightnesses predicted by an independent orbital model, a coincidence so improbable it would essentially require a planet to be there. The background source explanation would require the same alignment for 2 epochs, which is essentially impossible. A detection in August 2026 would force a conclusion. The candidate would become a confirmed planet. A clean non-detection in August 2026 would create a different kind of pressure. It would not by itself prove that a C1 was a fluke. The orbital framework would still admit families of orbits in which August 2026 was an unfavourable phase. Secondary windows extending through autumn might still yield a detection, but each successive non-detection would tighten the noose. If the planet failed to appear across multiple predicted windows, the team would face the choice between substantially revising the orbital parameter range, which would require many additional observations to find the planet again, or accepting that the August 2024 detection, despite the rigorous testing it survived, may have been an extraordinarily improbable statistical fluctuation that fooled every validation. Both outcomes advance the science. A confirmed detection adds Alpha Centauri A to a very short list, the catalogue of nearby stars with directly imaged planets, at the moment short enough to be memorized in an evening. A clean non-detection refines the techniques and the orbital models for the next attempt, and frees up substantial observing time for other priority targets. The team's own statements about the upcoming window have been careful. The papers refer to SAM throughout as a candidate. The press releases use phrases like strong evidence and promising. The community discussion has been described by various observers as cautiously optimistic. The case is strong enough to invest substantial observing time and to publish 2 papers in a major journal. It is not strong enough to claim a confirmed discovery. The team has been clear that the August 2026 observation will either confirm the candidate or force a major reassessment. What you're sitting inside as you listen to this is the closing window of a question astronomers have been asking for 70 years. From the late 1950s, when modern stellar spectroscopy first confirmed Alpha Centauri A as a solar twin, through the early radial velocity campaigns of the 1980s, through the dedicated near experiment of 2019, through the JWST observation of August 2024, the question has been the same. Does the closest Sun-like star to Earth have planets? Within weeks of you hearing this, the answer to that question, for at least one specific candidate, the Saturn mass body at 2 astronomical units, that the team has spent the past 2 years trying to confirm, will be known. The window of uncertainty closes within the same calendar year as this video. Some of you will hear it close before you watch. Some of you will hear it close while you watch. Some of you perhaps will watch it close. The orbital mechanics have already fixed the answer. The planet either occupies the predicted region in August 2026 or it does not. There is no continuum, no ambiguity, no probabilistic outcome that a future observation might eventually resolve. The instrument will execute. The data will exist. The result will be reported. You are listening to this in the small window of time between when the prediction was made and when the prediction is tested. Most cosmic stories never give you that window. Most cosmic stories are told after the fact, with the events sealed in the past and the meaning slowly extracted by generations of analysis. This story is being told in the act of being decided. You can almost feel the cosmic timing. You're sitting in the same calendar year as the answer. You may even be sitting in the same month. Hold that feeling for a moment. It is rare. And while you hold it, think about what the answer might mean. Not for the abstract question of exoplanet detection, for the much more particular question of what is out there at our nearest sun-like neighbour. Because if S1 is real, the implications go far beyond the existence of a single gas giant in the habitable zone of a single nearby star. They begin with what S1 itself might be, and they extend inevitably to what might be orbiting S1, because every gas giant we know carries its own miniature solar system of moons, and some of those moons in our own system are among the most promising candidates for harbouring life ever discovered. What would such a moon look like if it orbited S1? It would have 2 suns in its sky, and that is what the next part of this story is about. Part 8. Moons, 2 suns, and the habitability. Question. If S1 exists, it is uninhabitable. That is the first thing to say clearly. A gas giant with a mass somewhere in Saturn's range is not the kind of world where life as we know it could find a foothold. There is no solid surface. The atmosphere extends from a tenuous outer envelope to crushing internal pressures, with no boundary you could stand on. The chemistry of a gas giant's deep atmosphere, molecular hydrogen and helium under enormous pressure, with trace molecules of methane and ammonia, and water condensing into cloud layers at various altitudes, is not chemistry that allows the kinds of slow biochemical reactions life depends on. If S1 is real, it is a beautiful and scientifically valuable world, but it is not by itself a place where anyone or anything could live. Almost every interesting question about life in the Alpha Centauri system, if life exists there, points instead at S1's moons. Because every gas giant we know carries its own miniature solar system of moons. Jupiter has at least 95 confirmed satellites, including the 4 large Galilean moons named for the figures in Greek mythology, who attracted the attention of Zeus: Io, Europa, Ganymede, and Callisto. Saturn carries more than 270 known moons at the most recent count, which makes it the moon-richest world in our solar system. Uranus has at least 27, Neptune has at least 16. Even tiny Pluto, no longer counted among the planets, has 5 moons of its own. The moons of our solar system's gas giants are not minor objects. The largest, Saturn's moon Titan, is larger than the planet Mercury in diameter. It carries an atmosphere so dense that the surface pressure exceeds Earth's by about 50%, made primarily of nitrogen, with a substantial fraction of methane. Liquid methane and ethane flow across Titan's surface in rivers and pools in lakes the size of Earth's Great Lakes. The atmospheric chemistry is a slow industrial complex of organic synthesis, with photochemical reactions converting methane into more complex hydrocarbons that drift down through the orange haze and settle on the surface. Jupiter's moon. Europa carries an ocean of liquid water beneath its icy crust. The ocean is global, covering the entire surface of the moon under perhaps 10 kilometers of ice, and is estimated to contain more than twice the volume of all Earth's oceans combined. The water is liquid because Europa is heated from within by tidal flexing as it orbits Jupiter. The same gravitational forces that lock the moon's rotation also stretch and compress it during each orbit, and that mechanical stress heats the interior enough to keep the ocean from freezing. Saturn's moon, Enceladus, much smaller than Europa, also possesses a subsurface ocean. We know it does because we have seen the water erupting into space. Near Enceladus's south pole, 4 major fractures in the ice, called the Tiger Stripes, vent geysers of water vapour laced with salts, organic molecules, and small amounts of methane and hydrogen. The Cassini spacecraft flew through those plumes multiple times in the 2010s and sampled their composition directly. The water carries the chemical fingerprints of hydrothermal activity on Enceladus's seafloor, chemistry that, on Earth, supports entire ecosystems of life around deep ocean vents. None of these moons receive substantial light from their host star. Jupiter is more than 5 astronomical units from the Sun, more than 5 times farther than Earth. Saturn is more than 9 astronomical units out. The light reaching the Jovian and Saturnian moons is significantly dimmer than the light reaching Earth. The warmth that keeps Europa's and Enceladus's subsurface oceans liquid does not come from the Sun. It comes from tidal heating, the friction generated as gravitational forces from the host planet flex the moon's interior. The Sun, at those distances, is essentially a slightly larger and brighter star in the sky. Now imagine those same moons, scaled up and adjusted appropriately around S1. S1 sits in the habitable zone of Alpha Centauri A. The habitable zone is the orbital region around a star where a planet with the right atmosphere could maintain liquid water on its surface. For our Sun, the habitable zone extends roughly from the inner edge of Earth's orbit out to slightly beyond Mars. For Alpha Centauri A, which is slightly more luminous than the Sun, the habitable zone extends from approximately 0.9 astronomical units to about 1.5 astronomical units. S1, at an inferred semi-major axis of around 1.5 astronomical units and a substantial eccentricity, spends much of its orbit straddling the outer edge of the habitable zone and crossing into the slightly cooler regions just beyond. A large moon orbiting S1 would inhabit the same orbital region as the planet itself. It would receive its primary illumination not from S1, which has no significant intrinsic light, but from Alpha Centauri A, the actual Sun equivalent of the system. The radiation reaching the moon would be of essentially the same spectral character as the sunlight reaching Earth, the same photosynthetic wavelengths, the same warmth, the same yellow-white sky tone, attenuated slightly by whatever atmosphere the moon happened to have. That is unlike anywhere else we know of. In our solar system, the moons of gas giants exist in cold conditions because their host planets orbit far from the Sun. In the Alpha Centauri system, if S1 exists and carries large moons, those moons would inhabit a unique location in the catalogue of plausibly habitable environments. The only known case where a gas giant moon receives habitable zone solar-type radiation directly from its host star. The combination of solar-type radiation and tidal heating from S1 itself would produce conditions unlike anything we have a precedent for. Tidal heating alone keeps Europa's subsurface ocean liquid at 5 astronomical units from the Sun. The same tidal mechanism operating on a moon at 1.5 astronomical units from a Sun-like star would not just keep a subsurface ocean liquid, it would warm the entire moon, potentially allowing for liquid water on the surface in addition to subsurface oceans, depending on the moon's atmospheric composition and surface properties. Imagine standing on the surface of such a moon. You're on a body roughly the size of Titan, or perhaps slightly larger. The gravity is about 1/7 of Earth's, enough to keep your feet on the ground, but light enough that walking feels effortless, and a casual jump carries you several meters. The atmosphere is thicker than Earth's, with a chemical composition shaped by both the moon's tidal heat and the radiation from Alpha Centauri A. Perhaps it is nitrogen-dominated, like Titan and Earth. Perhaps it carries enough oxygen, generated by some local chemistry or biological activity, to be breathable. The horizon is closer than on Earth because the moon is smaller, so the visible curvature is more pronounced. Look up. The sky carries 2 suns. Alpha Centauri A, the primary, dominates the sky. From a moon at the habitable zone distance, the star appears almost exactly the same size and brightness as the Sun appears from Earth. The same yellow-white colour, the same disk diameter, about 1/2 degree across, the angular width of your little fingernail held at arm's length, the same warmth on your skin. If you closed your eyes and felt the sunlight, you would not be able to tell that you were not on Earth. But behind Alpha Centauri A, sometimes far enough away to be a separate object in the sky, and sometimes close enough that the 2 stars appear nearly together, sits Alpha Centauri B. A K-type star, orange in colour, slightly smaller and dimmer than its companion. From this distance, Alpha Centauri B would be brighter than any star ever visible from Earth except the Sun. It would cast distinct shadows. It would have its own daily and seasonal pattern of rising and setting, governed by the slow 80-year orbital dance of the binary. Sometimes the 2 suns would share the daytime sky. Sometimes only Alpha Centauri A would be up, with B having set below the horizon. Sometimes B would be high overhead while A had gone behind the horizon, providing a strange orange twilight that no Earth observer has ever seen. And behind the 2 suns, dominating an entire quadrant of the sky, would sit S1 itself. The gas giant would fill perhaps 1/4 of the sky from a close-orbiting moon's perspective, banded in the way Saturn is banded, with cloud structures running parallel to the planet's equator, perhaps with rings if S1 has them. The planet would go through phases like our moon does, illuminated by Alpha Centauri A and B and reflecting that light back at the Moon. The phases would be slow, governed by the Moon's orbital period around S1, but they would be among the most dramatic features of the Moon's sky. This is the cosmic next door, the closest plausibly habitable real estate humanity has any way to identify outside our solar system. We do not yet know if such moons exist. We do not yet know if S1 itself exists. The question of habitability is at this point fundamentally premature. We are speculating about moons around a planet that has not been confirmed. But the speculation is not idle. Every gas giant we know carries moons. The Alpha Centauri system, if it contains S1, almost certainly contains moons around S1 too. The architecture of planet formation produces moons as a near-universal byproduct of giant planet formation, and there is no reason to think Alpha Centauri's gas giants would be exceptions. If S1 is real, the moons are real. The only question is how many, how large, and what they look like. Whether any of those moons resemble Titan, or Europa, or Enceladus, whether any of them carry the conditions where life could plausibly arise, is a question we cannot answer with current technology. JWST cannot resolve individual moons of a candidate planet around a star 4 light-years away. The next generation of ground-based telescopes, the extremely large telescope coming online in the late 2020s, the Giant Magellan Telescope, the 30-meter telescope when its political situation resolves, will have substantially better angular resolution than JWST and might be able to begin separating moon signatures from planet signatures in certain favourable cases. Beyond that, the Habitable Worlds Observatory, currently in early planning stages, will be designed specifically to characterise the atmospheres of exoplanets in habitable zones around nearby Sun-like stars. Alpha Centauri A will be one of its priority targets. That is decades of work. It is the program for the next generation of astronomers who will inherit the foundations laid by Bateman's team and others working at the current state of the art. But here, in 2026, with S1 standing as a candidate awaiting confirmation, the moons are speculation. Beautiful speculation. Speculation grounded in our knowledge of how gas giants work and what kinds of satellites they carry. Speculation that is consistent with everything we know about planet formation and stellar systems. And speculation that hangs entirely on whether JWST's August 2026 observation finds the planet again. Because if the planet is real, the moons are real, the two-sun sky is real, and the question of life beyond the solar system has acquired a specific address at our nearest sun-like neighbour. If the planet is not real, then S1 was a beautiful and rigorously validated detection that nevertheless turned out to be something else. The question of planets around Alpha Centauri A would not be closed. The orbital model would simply have failed to capture S1's actual nature, and future observations with better instruments would continue the search. Either outcome reshapes the search for habitable worlds at our nearest neighbours. The August 2026 observation is the next pivot point, and while we wait for it, there is one more thread worth pulling on. The thread that asks, if S1 is real, what does that fact mean for everything we thought we knew about how planets form in binary star systems? Because Alpha Centauri A and B are not just a curiosity in the catalogue of stellar configurations, they are members of a class of stellar systems that, until very recently, planet formation theory predicted should not host planets at all. If S1 exists in that environment, the theory will need to be rewritten, and the rewrite will have consequences that reach to roughly half the stars in the galaxy. Part 9. What S1 rewrites. For most of the past half-century, the dominant theoretical assumption about planet formation in tight binary star systems has been pessimism. The reasoning was straightforward. Planets form from disks of gas and dust that orbit young stars in the first few million years of stellar life. The disk material gradually clumps under its own gravity, growing pebbles into boulders, boulders into planetesimals, planetesimals into protoplanets, and eventually into the planets and moons we see today. The process is well understood for single stars. It produces something like our own solar system, with a mixture of rocky inner planets gas giants further out, and a population of smaller bodies extending outward through the Kuiper belt and into the Oort cloud. In a binary system, the same process has to operate in the presence of a second star, and the second star is, gravitationally speaking, a wrecking ball. Its gravity pulls on the protoplanetary disk material in ways that disrupt the smooth accumulation. If the binary companion is far enough away, many hundreds of astronomical units, the disruption is minimal, and the inner system around either star can essentially form planets the same way a single star does. But if the binary companion is closer, an Alpha Centauri B at 11 to 36 astronomical units from A is much closer than that comfortable threshold. The disruption becomes severe. The disruption takes several forms. The most basic is disk truncation. The companion's gravity prevents the protoplanetary disk from extending out as far as it would around an isolated star. The disk is essentially cut off at some maximum distance, with material beyond that distance scattered by the companion's gravity. For a binary like Alpha Centauri A and B, simulations have predicted that the protoplanetary disk around each star would be truncated at perhaps 2 to 4 astronomical units. That leaves room for inner rocky planets, and possibly Earth-mass worlds in the habitable zone. But the available material for forming gas giants, which require large amounts of nearby gas, is much more limited than around an isolated star. The second form of disruption is planetesimal scattering. As the disk material starts to clump into kilometre-scale planetesimals, the building blocks of future planets, those planetesimals begin to orbit their host star. In a binary system, the companion star's gravity perturbs those orbits over time, exciting them into more eccentric and inclined configurations. When two planetesimals collide at high relative velocities, which the binary perturbations enforce, they tend to shatter rather than merge. The accumulation process that grows planetesimals into planets reverses itself. The planetesimal population is ground down faster than it can grow up. The third form of disruption operates on the longer timescale of fully formed planets. Even if planets manage to complete their formation despite the binary perturbations, their subsequent orbital evolution is affected. Planets on certain orbits are slingshot out of the system within a few million years. Planets that survive are pushed into more eccentric configurations by ongoing gravitational interactions with the binary companion. The architecture of the planetary system that emerges is constrained, sometimes severely, by the binary's geometry. For decades, the consensus from these theoretical considerations was straightforward. Tight binary systems should be hostile environments for planet formation. The Alpha Centauri system, with its main pair orbiting at separations comparable to the Kuiper belt's outer edge, should be particularly inhospitable. Planet formation simulations consistently predicted that planets around Alpha Centauri A and B would be small, rocky, and confined to orbits well inside 1 astronomical unit, where the binary perturbations are weakest. Gas giants at 2 astronomical units, like S1 if it exists, should be impossible. The required disk material is not available. The required dynamical stability is not there. S1, if confirmed, is a problem for that consensus. It is not that the theory was completely wrong. The theory correctly predicts that gas giants in tight binaries should be rare, and that the planetary systems around such binaries should look different from the systems around isolated stars. But the theory's specific claim that gas giants in the habitable zone of 1 star of a tight binary should not exist fails if S1 is real. The implications of that failure propagate outward. The theory was not just a statement about Alpha Centauri. It was a statement about the broader population of binary star systems in the galaxy. Roughly half of all Sun-like stars in the Milky Way are members of binary or multiple systems. Many of those binaries have separations comparable to, or even tighter than Alpha Centauri. If the theoretical predictions about planet formation in such systems were correct, those binary systems should be largely planet-free, at least in the orbital regions where the binary perturbations are significant. SE1 says the predictions were overly pessimistic. Some window of stability exists that the simulations have missed. Some formation mechanism allows gas giants to accumulate in environments where the simulations say they should not. The specifics of that mechanism are not yet clear. Several possibilities are under active investigation, including formation in a thicker, more vertically extended disk than current simulations assume, formation through gravitational instability in the disk rather than through the slower core accretion process, or formation at a more favourable orbital distance with subsequent migration into the observed position. Each possibility predicts somewhat different demographics for binary system planets, and somewhat different observational signatures that future surveys could test. The number of stars potentially affected is enormous. The Milky Way contains roughly 200 billion stars. Perhaps 100 billion of them live in binary or multiple systems. If even a fraction of those binaries are similar to Alpha Centauri in their planet formation properties, the population of habitable zone planets in the galaxy expands substantially beyond what current census estimates assume. Every prior survey that excluded binaries from habitability calculations would need to be revisited. The exclusion has been the standard assumption in most exoplanet population studies, including the well-known estimates that the Milky Way contains tens of billions of potentially habitable Earth-sized planets. Those estimates focused on single stars or wide binaries because that was where the theoretical framework was most secure. If tight binaries also host planets, including planets in habitable zones, the estimate of habitable planets in the galaxy may need to be revised upward, perhaps significantly. The Bachmann team's papers explicitly point at this implication. The discovery, if confirmed, opens a door that exoplanet astronomers have largely treated as closed. The technical implications are equally important. The blind offset method developed for Alpha Centauri A is now a validated tool in JWST's repertoire. Other nearby bright stars that were previously unobservable because of brightness saturation are now potential targets. The team has identified several priority candidates for follow-up. Tau Ceti, 12 light-years away, has been the subject of radial velocity hints suggesting multiple planet candidates for years. JWST observation using blind offsetting could now attempt direct imaging of those candidates. Epsilon Eridani, 10.5 light-years away, hosts a confirmed debris disk that suggests an active planetary system in formation. 70 Ophiuchi, 16 light-years away, is structurally similar to Alpha Centauri, a tight binary of Sun-like stars that should now be amenable to the same observation technique. Each of those targets, observed with the technique pioneered for Alpha Centauri, could yield candidate planets that would have been undetectable with prior methods. The Alpha Centauri observation, regardless of how S1 itself resolves, has permanently expanded what JWST can do. There is also a longer-term implication that points beyond JWST. The extremely large telescope, currently under construction on Cerro Armazones in Chile and scheduled for first light in the late 2020s, will have a 39-metre primary mirror, roughly 6 times the diameter of JWST's primary, with proportionally greater light-gathering area and angular resolution. The Giant Magellan Telescope and the 30-metre telescope, with primary mirrors of 25 and 30 metres respectively, will offer comparable capabilities. Each of these future instruments will have direct imaging sensitivity sufficient to reach Earth-mass planets around the very nearest stars. Alpha Centauri A will be one of the earliest priority targets for each of those instruments. The JWST detection of S1, if it survives the August 2026 confirmation window, will provide those next-generation observatories with a calibrated target whose orbit will be partly known by the time they come online. The S1 candidate, once it transitions to a confirmed planet, will be observable in unprecedented detail. Its atmospheric composition could be measured through spectroscopy across many wavelengths. Its temperature could be tracked through the orbital cycle. The presence and orbits of any large moons could begin to be constrained, though confirming individual moons will require the sensitivity of the Habitable Worlds Observatory in the 2040s. A decade from now, in other words, Alpha Centauri A may be the most thoroughly studied exoplanet host in the sky. The JWST detection of August 2024 is the first step in a long process of characterization that will continue for the rest of the 21st century. The detection is not an endpoint. It is the beginning of a sustained scientific engagement with our nearest Sun-like neighbour. That engagement matters because Alpha Centauri is, and will remain, 4.37 light-years away. It is the place an interstellar probe, if such a probe is ever built, would visit first. It is the place humanity has, in some sense, always already been planning to go. The Breakthrough Starshot concept proposes gram-scale spacecraft accelerated to 20% of the speed of light by laser propulsion, reaching Alpha Centauri in 20 years of flight time. That concept is currently more aspiration than engineering, but it exists because Alpha Centauri is the natural first destination for any interstellar mission. The more we know about what is there, the better positioned we are to design such missions and to interpret their results when they arrive. Every observation of Alpha Centauri in this sense is preparation. Preparation for the moment, perhaps decades or centuries away, when humanity sends instruments to the system that can return data directly. The JWST detection of S1, if it survives confirmation, provides the first target. The next generation of telescopes will provide detailed characterization. The interstellar missions, when they happen, will close the loop. 4 light-years away, the cosmic front porch, the place we are still, even now, only beginning to see clearly. And the question of whether we have seen the first planet there, clearly, unambiguously, in a way that survives every check the team can run, will be decided this summer, 8 weeks from now. The cosmic timing is, in its way, almost gentle. We have been asking the question for 70 years. The answer arrives within the same calendar month as the beginning of autumn. Part 10. The Unresolved Ending. So we come back to where we started. 4 light-years away, almost exactly identical to our Sun in every measurable property, sits Alpha Centauri A, the third brightest star in the southern sky, the cosmic front porch. For 70 years, astronomers have asked whether it has planets. For most of that time, the answer was the same. We do not know. We cannot tell. The technology is not sufficient. Then, on August 14, 2024, an extraordinary observation was executed by a team that had spent 7 years preparing for the attempt and 12 months recovering from an initial failure. The James Webb Space Telescope, never designed for this kind of target, was carefully aimed using a blind offset procedure that no other instrument in history could have accomplished with comparable sensitivity. The mid-infrared instrument's 4-quadrant phase mass coronagraph engaged. 10 hours of integration time were collected. Months of data reduction stripped away the contamination from one of the brightest stars in the sky, from its binary companion, from the diffraction structures of Webb's hexagonal primary, from the dense background of galactic plane sources, and in the cleaned image, at 1.75 arcseconds east of Alpha Centauri A, at a position consistent with about 2 astronomical units of physical separation, a faint point of light remained, 3.5 millijansky at 15.5 micrometers, effective temperature around minus 48 degrees Celsius, mass in Saturn's range, statistical significance 5.5 sigma, less than 1 chance in 10 million of being random noise. The team designated it S1. For 70 years, astronomers had hoped this number would one day exist. The number existed now. Then, between February and April 2025, S1 disappeared. The follow-up observations executed cleanly. The instrumentation performed within specification. The pipeline ran identically to the August reduction, and the field where S1 had blazed at 5.5 sigma was empty. Nothing at 3 sigma, nothing anywhere. The case of a disappearing planet, as Aniket Sanghi named it. Then came the orbital reconciliation. The team built a simulation framework that searched the parameter space of dynamically stable orbits, consistent with the August 2024 detection, and the 5-year prior near detection of C1 at 1.1 arcseconds. Out of millions of synthetic orbits, the surviving family clustered at eccentricity around 0.4, inclination relative to the binary plane between 50 and 130 degrees, period between 2 and 3 years. Eccentric, inclined, the orbit of a survivor. And of those surviving orbits, 52% naturally placed the planet at undetectable positions during the February and April 2025 epochs. The disappearance was not evidence against the planet. It was the most probable outcome given the orbital geometry. The orbital model also generated a forward prediction. The next favourable observation window, when S1, if real, should be approaching a pastron again and become visible to Miri, falls in August 2026. The team submitted their results for publication in the Astrophysical Journal Letters and prepared to wait for the predicted window. That window is approximately 8 weeks from now. I want you to sit with that for a moment. You are listening to a story whose ending does not yet exist. The data that will decide it has not yet been collected. The observation has not yet been executed. The pipeline has not yet been run on the August 2026 measurements. The teams in Baltimore and Pasadena are, as you listen to this, finalizing their plans. The reference star Epsilon Muscae is rising over the southern sky each evening, completing its slow path across the cosmos, available as the anchor for the next blind offset acquisition. The detectors in Miri are at their operating temperature, cooled to a quarter the temperature of Pluto's surface, ready for the next set of photons to arrive. By the time some of you finish watching this video, the August window will have opened. By the time others of you watch it later in the year, the answer may already be in the news. The story will divide its audience in time. Some of you will hear it before the data exists. Some of you will hear it after the result is known. The video, once posted, will sit at a fixed location in the timeline of this story, while the world moves through the moment of resolution at its own pace. This is unusual. Most videos this channel produces tell stories about events that finished long ago. The death of stars, the formation of galaxies, the detection of signals decades in the past. The S1 story is structurally different. The central event of the story, the observation that will either confirm or refute the candidate, has not yet happened. You are inside the window. The cosmos is currently in the act of answering a question that has been open for as long as exoplanet astronomy has existed. When the answer comes, it will not be ambiguous. A detection in August 2026, at the predicted angular separation, at the predicted position angle, at a brightness consistent with the August 2024 signal, would essentially close the case. 2 observations across 2 years at orbitally consistent positions, supported by a 5-year prior precursor at the same orbital family, would together rule out the alternatives that the team has been unable to fully eliminate from a single epoch. The candidate would become a confirmed planet. The closest Sun-like star to Earth would have its first directly imaged world. Alpha Centauri A would be added to a small, memorizable catalogue of nearby stars whose planets have been seen directly, not just inferred from indirect signals. The catalogue as of today contains only a handful of stars. Alpha Centauri A would be the closest member by a wide margin. A non-detection in August 2026 would not be a definitive refutation. The orbital model would still admit some families of orbits in which August 2026 was an unfavourable phase. Secondary windows extending into autumn might yield a detection, but each successive non-detection would tighten the case against the planet's reality. The team would face the choice between substantially revising the orbital parameter range, requiring more observations to find the planet again, or accepting that the August 2024 detection, despite the rigour of its validation, may have been a statistical fluctuation so improbable that it managed to fool every test. Either outcome advances the science. A confirmed planet would rewrite parts of planet formation theory and add the closest Sun-like star to our catalogue of known planetary systems. A clean non-detection would teach us something important about the boundary between what direct imaging can prove and what it cannot, and would refine the techniques for the next attempt at this and other nearby stars. What you cannot do, as the listener, is force the answer to come in any particular form. The orbital mechanics have already fixed it. The planet either occupies the predicted region of the sky in August 2026, or it does not. There is no middle ground that future analysis might gradually resolve. The instrument will execute, the data will exist, the result will be reported. Hold the strangeness of that. The questions that astronomy normally lets us ask are questions whose answers, even when they are unknown, are in some sense already determined. The supernova has either occurred or it has not. The galaxy has either formed or it has not. The black hole has either merged or it has not. The cosmic answer is fixed. Only our knowledge of it is incomplete. What is unusual about the Ezron story is that the question of our knowledge has a deadline. The window between asking and knowing has a closing date. You're sitting in that window. For 70 years, the question of whether the closest sun-like star to Earth has planets was an open scientific question waiting for instruments capable of answering it. The instruments are now built. The observations are now scheduled. The orbital predictions are now precise. The window between asking and knowing closes within the same calendar season as this video. It might close before some of you finish hearing it. It might close after. The cosmic timing has, in its way, given us a particular moment to sit inside. The small slice of time between when the instrument's prediction was made and when the instrument's prediction is tested. If S1 is confirmed, the next decade of exoplanet astronomy will look different than it would have. The blind offset technique will spread to other bright nearby stars. Tau Ceti, Epsilon Eridani, 70 Ophiuchi will become tractable. Planet formation theory will be reworked to accommodate gas giants in habitable zones of tight binaries. The Habitable Worlds Observatory of the 2040s will inherit Alpha Centauri A as one of its first targets. The Extremely Large Telescope and the Giant Magellan Telescope will image S1 in detail it would otherwise have lacked. Conversations about interstellar missions will, for the first time, have a confirmed planetary target at a confirmed distance with confirmed atmospheric properties, not just a star whose planetary system was speculative. If S1 is not confirmed, the field will refine its techniques and continue the search. The Bachmann team will not, by any reasonable expectation, give up. The next campaigns will go forward. The instruments will get better. Future direct imaging telescopes will achieve sensitivities that JWST cannot. The question of whether Alpha Centauri A has planets will remain open until it is decisively answered. Either way, you have been here for the asking of the question. That is something. In a universe as large as ours, at distances as great as the 4 light-years to our nearest sun-like neighbour, having been present during the asking of a question is not nothing. The light from Alpha Centauri A that will be collected by JWST in August 2026 is, as you listen to this, already on its way. It has been travelling through interstellar vacuum for the past 4 years. It is currently somewhere between the Alpha Centauri system and L2, somewhere out there in the dark between us and our cosmic next door. By the time it arrives at Webb's primary mirror, you will probably be asleep on some other night, or going about some entirely unrelated part of your life. The light will not announce itself. It will simply arrive, bounce through the optical system, pass through or be blocked by the coronagraph, and either contribute to a detection or not. A few weeks after that, the data will be analysed, and we will know. For 70 years we did not know. Tonight, we still do not. By the end of this summer, we will. The cosmic timing is exquisitely arranged. The asking and the answering are about to meet, on a calendar week that no human being today can predict precisely, but that everyone today can place to within a few weeks. Get cozy. Drift if you want to. The light has been travelling for 4 years. The window opens in 8 weeks. The answer is coming on its own schedule, and whatever it turns out to be, our nearest sun-like neighbour will, by the time you next think about it, no longer be a place we are asking the question about. It will be a place we know.